Okay, so rates of change in particle motion 1. That implies there's going to be a particle motion 2 later on in the year. Alright, so what we have here is rates of change, and today the key word is going to be units. Units are extremely important. Alright, so this is something that you can read here, but basically what we're saying is what we said in the beginning of the year. Calculus is change. So the real idea behind a derivative is to tell us how fast something is changing at any moment in time. Alright, so we have an example here. The temperature, T in degrees Fahrenheit, of a cold yam. Everybody loves yams, right? Alright, placed in a hot oven is given by temperature, which is a function of time, where T is minutes since it was put in the oven. So what does this mean, f of 20 equals 255? Okay, well, T is our time, so when we write this, we're going to try to use the same format for each one. At T equals 20 minutes, and it's important to put all these units in here. At T equals 20 minutes, comma, what does that 255 mean? Well, it says that the function is a degrees in Fahrenheit of a cold yam placed in the oven. So, at T equals 20 minutes, the yam's temperature is 255 degrees Fahrenheit. So that's exactly what that means, okay? In words here. So we take a shortcut with math, f of 20 equals 255. But we know that means at T equals 20 minutes, the yam's temperature is 255 degrees. Alright, if we were going to plot like a little graph here, time would be our independent variable, and then we would have degrees Fahrenheit when we graph it. Okay, and so it's kind of going to rise, and it's just going to kind of hover right there at 255. Alright, so if we talk about what is the sign of f prime of T, alright, how is the temperature changing? Well, the temperature is increasing, okay? It's going up. We put a cold yam in a hot oven, the temperature is going to go up. Alright, so the sign of that would be positive, and that's because our temperature is increasing. Alright, our temperature, or if you want to think about it, f of T, our original function, is increasing. Increasing, okay. So then we have, what are the units of f prime of 20? Well, f prime, remember that's the slope of this, so that's our change in our y over change in x. It's change in the temperature in degrees Fahrenheit over time. Alright, so degrees in Fahrenheit, alright, degrees Fahrenheit over time, which in our case, time is measured in, what is that, hours, minutes, okay? Degrees Fahrenheit over minutes. Those are the units of our slope here, or our derivative. And what's the practical meaning of that statement? Well, again, we're looking at a specific time. So at T equals 20 minutes, okay, 20 minutes, f prime of that equals 2. So that's our rate, our degrees per minute. So, and the wording is tough here. This is something that we have to learn to work on together. Alright, so at T equals 20 minutes, the yam's temperature and it's positive, right? It's increasing. And how fast is it increasing there? And that's given by our f prime of 20. It's increasing at 2, alright, degrees Fahrenheit per minute. Okay, so the wording, you have to be really careful with the wording. The practical meaning is, at T equals 20 minutes, the yam's temperature is increasing at a rate of 2 degrees per minute. Okay, so remember, derivatives are rates, and that's going to keep continuous. That's going to be that same idea all year long. Okay, let's try a different one here. So we have an ice cream company. Everybody loves ice cream. Alright. My favorite's mint chocolate chip, so I'm going to use green on this problem. So the cost in dollars to produce K quarts of cookie dough is given by this equation here. So if f of 200 equals 70, 200 tells us the number of quarts there. Alright, so and 70 tells us the cost in dollars. So what are the units of the 200? Well, that would be quarts, right? And what are the units of the 70? Looks like that would be dollars. So explain clearly what this equation is telling you. And here the wording is kind of tough. But we would say at, we always want to start this about the same. At the 200 quart time, or the 200 quart, let's sound fancy here, production level. It's easier to write in cursive. Alright, at the 200 quart production level, the cost, right, the cost in dollars, the cost to produce it, or just the cost, is $70. So if we only make 200 quarts of cookie dough ice cream, then it's going to cost $70 to produce that. Alright, and again, if I want to draw a quick little picture, I know my independent variable here is Q. That's giving me the number of quarts. And then we have the cost in dollars. So now as we look at the derivative, f prime of 200 is 3. So the units of the 200 again are quarts. The units of the 3 though, okay, this is talking about the slope of this. So it's dollars per quart. Dollars per quart. Okay, the meaning of this. So again, at the 200, and if you could figure out a better way of wording this, you tell me. At the 200 quart production level, I'm going to abbreviate this because I already wrote it once. At the 200 quart production level, comma, the cost, and since the 3 is positive, the cost must be increasing. Okay, you always want to specify if it's increasing or decreasing, and you can tell that just by the sign. Alright, the cost is increasing, okay, by, and how much is it increasing by? It looks like it's going to be $3 per quart. Okay, that says quart there. It's kind of hard to understand, but that's okay. So again, look at these notation that we're using and the meaning. That's the hardest part of this, trying to figure out what it means. And the more we practice that, the better you're going to get. Okay, let's try example 3 now. Let f of t be the number of centimeters of rainfall that's fallen since midnight. T is in hours. So we're going to interpret these in practical terms, giving units. Okay, so T is 10. So at 10 hours. Okay, we'll always write that at 10 hours. And then the 3.1, our function value represents the number of centimeters of rainfall that have fallen since midnight. We could say 3.1 centimeters. So at the 10-hour mark, or aka 10 a.m., if you want to write that, that's okay. Alright, maybe I should write this too. At t equals 10 hours, or 10 a.m., 3.1 centimeters of rain have fallen. Okay, and if we draw like a graph of this, our time here is our independent variable, and then it tells us that the number of centimeters of rain, F inverse, okay, F inverse, that's what that means there, F inverse. And of course you guys remember from pre-calc, inverse functions, you're kind of just switching that x and the y value. So F inverse, if I draw a quick little graph, instead of having time in hours, let's put that over there, and as our independent and centimeters as our dependent, we're switching it. So now we have centimeters and hours. So at, and what do we have here? or maybe not at, maybe this is better, when 10 centimeters of rain have fallen. So right at that point when 10 centimeters of rain have fallen, then 16 hours have passed. Okay, because time's accumulating here. When 10 centimeters of rain have fallen, then 16 hours have passed. It's like the opposite of what we did before. That's what an inverse function is. Alright, if we go to part C, we are talking about now f prime. F prime, remember that would be the slope of this. So we're going to be talking about centimeters per hour. So at t equals 8 hours, or 8 a.m., whatever one you want to think about. Now we have a positive derivative value. So at t equals 8 hours, rainfall, I guess what you could say, rainfall, has increased, or is increasing, let's say that. Oh man, okay, forget that. Rainfall is increasing, because it's still increasing. And how fast is it increasing? By 0.4 centimeters per hour. So it's raining harder at that time than it was right before it. Okay? So then let's look at the next one. We have, whoa, look at all that. F inverse prime of 5. Okay, so then that's this F inverse. Okay, so F inverse prime, our units are going to be hours per centimeter. Okay, hours per centimeter. So we have, this time, let's see, how do we word this? When 5 centimeters of rain have fallen, okay, right at that point, let's see, this is hours per centimeter, so we could say maybe time is passing and it's passing by, alright, 2 hours per centimeter. So the wording's kind of rough there. Again, if you could think of a better way of saying that, let me know. So when 5 centimeters of rain have fallen, time is passing by 2 hours per centimeter. So it's like it's taking 2 hours for each centimeter of rain to fall at that point when 5 centimeters have accumulated. Alright, and again, we're going to work with this, so don't worry if you have a few questions. Anytime, you know how we say tangent line, we think derivative right away. Okay, if we think secant line, that's like an average rate of change. If I just say rate of change, you have to know that I'm talking about instantaneous. And right there, the derivative. Okay, exactly. And this is the last example I'm going to go over today. So we have the radius of a circle is increasing. How fast is the area changing with respect to each of these? Okay, how fast? That's a rate. So how fast is it changing? Well, of course you guys all remember this. Area equals pi r squared. Okay, and we want to know how fast is it changing. So we're talking about the derivative. And I'm going to write it in both forms. It's changing with respect to its variable r, okay, or a prime of r. The derivative of that, now pi is just a constant, so it's going to be 2 pi r. So we're going to evaluate it, and I'll write it both ways. Evaluate it at when the radius is 5. So if we plug that in, we're going to get 2 times 5 times pi. So that's 10 pi. Anytime you see word problems, you probably have to describe it in words. Alright, so so we could say when the radius, okay, when the radius is 5 centimeters, or 5 inches, sorry, stuck on that centimeters of rain. When radius is 5 inches, okay, the area is How's it changing? Well, it's positive, so it's increasing. The area is increasing by, okay, and so now we got to figure out the units here. We know it's 10 pi, but what are the units? If you use this a prime of r form, it's kind of hard to think about the units, but this way it kind of tells us, well, area would be in inches squared, and the radius is in inches. So don't be afraid of this form because it might be more helpful. It tells you what the units are. Alright, so the area is increasing by 10 pi square inches per inch. So each inch is growing by 10 pi square inches. It's getting bigger, faster. Alright, and this the same thing at 10, so I'll just write it in using the alternate form here. A prime of 10, if we plug it in, it'll be 10 or 20 pi. In this case, it would be when the radius is 10 inches, the area is increasing by 20 pi square inches per inch. Alright, and we have one more part to discuss. How fast is the circumference changing at these times? So the circumference is given by 2 pi r. So if we take the derivative of this, c prime of r, alright, or I'm going to also write it this way, dc dr, then that's just going to be 2 pi. It's going to be a constant value. Alright, so let's just write the words here and we'll finish up. When the radius, sorry about that, when the radius is 5 inches, comma, okay, the circumference is it increasing or decreasing? And this is positive, so it's increasing. And what kind of units are we talking about? Well, the circumference given with inches and the radius is given with inches, so we're just going to say inch per inch, because if you don't put that, then we're all going to think you forgot it. So it's increasing by 2 pi inches per inch. Okay, and so let me know tomorrow in class if you guys have any questions. It's helpful to discuss this with someone. Alright, have a good one.